Okay, in this video I want to talk a bit about the DBR01-X, which is the Happiness Firing System's master module for controlling DB04s, 04Rs, and the other modules such as their 12Q modules. This is supposed to be sort of like the end solution to complete control over your devices, and it works by splitting up all the devices into what they call districts. Each district has 12 queues plus the special function queues, which is fire, all fire, and sequence fire. These districts on their master controller run from 0 to 99, so that's 100 districts. So that effectively gives you the 1200 queues. And that can again be split over the DB04Rs or their 12Q modules, or I think any type of module they sell, any queue numbers can be programmed to this module. So what I want to do is have a little look at this and talk about districts, how they work, how I think they run districts, and then we're going to do a few question marks because there's still some stuff that I want to research, and then I'll come back and do another video on my findings if there's anything of interest. So first of all, let's look at the actual controllers to give us some hints of how this could be working, because I don't have one, so I can't tear one down obviously. So their description has a few key points in it which I think we should just quickly have a look at. So they mention obviously 1200 queues by the districts, and this last bit here I think is the interesting part. All receivers in the district will fire sequentially at 0.4 seconds interval. If you need to change the interval, please tell us when you place the order. So they're clearly programming the controller now to effectively transmit the delay times that they're going to fire between queues in a district, whereas previously on the first gen modules that delay time was already programmed into the module, into the DB04R. So the master module couldn't overwrite that. They've changed that by the looks of it now, that you actually program it from the transmitter, or they program it from the transmitter, sorry. So it no longer does the DB04R have that fixed timing. And we sort of know this because when we did the teardown of the third generation modules, Q13, 14, and 15, which are the special function queues on the first gen, didn't work on the third gen. So they obviously removed those functions from the third gen, or at least from those queue numbers, because I'll talk a bit about this in a second, about what I think they may have done now. So we know the controller is doing a bit more than what it used to do. Let's move on. So the next few slides are from a screen grabs from a video by DIY Pyro, and I've put the YouTube link up on top of my video just as a disclaimer. So these are not my photographs, these are hers photographs, I believe, photographs from his video. So this again is the older module. This one looks different if you notice from the one that I showed you from the very start of the video. This is their older version, but this is the only one I can find where somebody's taken it apart, and I believe they'd be very similar, because if you look at how it runs in a second, you'll see the same functions and that still exist. So I don't see any reason why they'd change the hardware that significantly. So on the back, as you can see, this is the front panel turned over. Obviously we have our buttons at the bottom over where his finger is, and then we have this small PCB and then the battery pack. So there's the battery pack, there's the PCB obviously, and there's the 4 buttons. So if we actually now have a look at the PCB itself, because this gives us some really good clues about what they're doing here. So if we look, starting from the bottom, so underneath his fingers and thumbs are the inputs from the buttons. Then above that we can see all these orange components, which are all diodes. That tells me that they are using effectively diodes to work out the binary for these buttons. So they've got 14 buttons. So they've got the 12 queues plus all fire and sequential fire. So they're going to then arrange these diodes, I believe, that it changes those 14 buttons into a 4-bit binary pattern, which the microcontroller will watch out for, will listen to. So they use 4 inputs on the microcontroller, and those 4 inputs are the binary equivalent weightings of the switches being pressed. And we've seen this before. The remote teardown I did used exactly the same principle. they used diodes to then create this bit pattern. The reason why you've got to use diodes obviously is because effectively you're joining switches together, so you don't want to end up shorting switches out in the process of doing that, so you have to control that by using diodes. And there's numerous names for this principle of using diodes. So then moving on upwards, we have a smaller chip next to the larger chip, which is going to be, of course, the I2C memory for the microcontroller. That's not going to hold the program. That's going to hold the user definable parts that the factory probably want to put into the controller, maybe for the client, which they don't want to have to burn into the microcontroller during manufacture. So this might contain things like the cue timings for the sequential file, which I've already mentioned that you can change by telling them and they'll reprogram the module for you. It will also contain the bit pattern of the unique identifier for this controller, so that more than one controller doesn't end up controlling the same set of modules. And I'm sure there's a couple of other little bits they'll put on there. And above that, we obviously have a much bigger microcontroller than the one that's in the DB04R modules. This will also be, you can't quite see it on the screen here, but underneath here is a 7-segment display, which they're using for showing you the districts. In the newer version, they've got rid of the 7-seg and they've just got some little rotatory buttons that will give you set your value, some rotary encoders possibly. That will lessen, of course, the pin count on the microcontroller so they can get away with a smaller microcontroller. And then next to this final little outbreak board here is, of course, the RF module. And you'll notice that the RF module does not have any sort of chipset, encoding chipset driving it. It's being driven most likely directly. It looks like some of these traces here go directly over to the microcontroller, which means the microcontroller can send any bit pattern it likes from the transmitter, and that's important because we'll discuss that a little bit later in the video. Then up here we have some blank components, some non-populated components, which looks to me like it could be another RF circuitry. Maybe they were thinking about, maybe first they couldn't get this module anymore, they might have to make an onboard solution, or maybe they're experimenting with an onboard solution, then went with the other solution. I'm not quite sure. It does seem a little bit weird. What also seems a little bit weird, and maybe it's because I can't see what's on the other side of this board, is we have these massive pads here going through the middle. I'm not quite sure what they're connecting to, but oh well. So if we move on, before we carry on the rest of the video, I just want to quickly remind you of the memory allocation which we got from the teardowns. So in the first gen module, the first 2 bytes of memory that had the 092E, we could never figure out what that was referring to. It read that from memory, but never seems to actually do anything with it. Then the next 3 bytes was the actual controller unique code and the queue start, because don't forget, on the first gen modules you couldn't program individual queues, you just programmed the start queue of the first queue. So obviously this one, CC09A, is the unique identifier of the remote, and then 9 is the queue starting. So that module would go 9, 10, 11 and 12. In the third gen, it changed slightly. So now from 00, they're doing it in queues. So the first 3 bytes is queue number 1, the second 3 bytes is queue number 2, and so on and so forth. So that's Q1, Q2. I messed that up, sorry. That should be there. Q3, and then Q4 is there. And you can see that not only is it recording the queue number, it's also recording the bit pattern of the security chip on the controller. So in this case, it's a different remote control, unfortunately, from my previous teardown. So this remote control ID was 1E231, and then the last number is the queue number. So in this one, you see Q1 is 1, Q2 is 2, Q3 is 3, Q4 is 4, and of course you could change this. In this generation, you could change these queues to be any number they like and any remote they like, because it's storing all that data on every queue. Whereas the first gen, the controller was fixed, because once you'd recorded from one remote, that remote was the only value it held for all the queue numbers. So you could only use one remote for those first gen modules. But then at the end of the third gen, a little bit similar like we had on the first gen, we have 8 bits that I have not found a reason for as of yet. And I'm beginning to think this is where they may be hiding the special functions such as the all fire function, because the problem you've got with the all fire function is that obviously you have 12 queues firing simultaneously, and if you did that very quickly sequentially from the controller, I think you would still struggle to transmit enough data quick enough and for each module to receive it quick enough and process it quick enough that all 12 channels, all 12 queues fired together. I think you'd end up with delays. So I reckon there still is the all fire function built into the third gen, but I haven't figured out yet how to access it. And I'm going to experiment a bit more with these last 8 bytes, to figure out if I can use them to access the special functions. And again, this may link back into the first gen where they had the 09 and 2E on the first 2 bytes, because we never really figured out what they went either. They're obviously important. And I will look at my other modules and see if it's all the same, see if it all are 09 2E, or whether that's unique to the module or not. So in terms of why these look like they do, it's just because obviously on my modules they're programmed for the 12-key remote, and the 12-key remote uses the EV1527 chipset within it, and this is the format that it uses. There's a preamble that obviously is not recorded because that's just for the radio receiver to realize that there's an incoming message. Then you have the C0 to C19, which is the security code. So that is the CC09A. That is those 2.5 bytes. And then the last 4 bits, the last nibble, is of course the data, which in our case is the queue number. But this obviously is using this particular chipset. And we know the DB04Rs take this format because it's in their memory. And I've noticed that when you actually press queues and the DBR04R receives them, it's looking for those specifically memory allocation areas to figure out the queue. So if I go back a minute, so on the third gen, it is looking at memory address 00 and reading to 02 for the data for the first channel. Always does that. Then it always reads 03 to 05 for the second channel. So these are fixed programs. It's been told it needs 3 bytes of data, and it's been told where these memory addresses are to get it. So we know that it has to use 3 bytes. Or, it could use less, but it can't use more than 3 bytes, maybe is a better way of saying it, in order for it to function. So now, if we now experiment this, we can figure out how they may be doing this. So what if we removed one nibble from the security code and you made that the districts? Now effectively you have a district then queue. So you have district nibble then queue nibble. That would give you 15 or 16 districts. Because you've got 0 to 15. That would still give you 65,000, over 65,000 security combinations for each module. But again, that doesn't give us the full amount we've got. So we could go more than that. If you wanted to get the full 100 districts that they claim they can, we've got to have a whole byte. But they're not using the whole byte, which is really interesting. The reason we're not using the whole byte is because obviously their encoder only goes from 0 to 99, and they don't want to put another digit on, because then they couldn't use the full amount of digits effectively, because obviously that would then go up to 999, which, on a 1 byte you've only got up to 255. So I think they've deliberately limited the encoders for 0 to 99 because then that means they just get those two numbers, and you can use them for full extent on the module rather than have loads of queue numbers you can't, district numbers you can't use. So we've got 1 byte, which is our district, then we've got a queue, and we've got 1.5 bytes of security code. So that still means we get over 4,000 security combinations per master module, which is not bad. So to me, this looks like how they're going to be doing it. They're going to be using this idea of breaking the 3 bytes down further. So you still have the queue nibble, because that is realistically what the DB04Rs are programmed to look at. They look at that last nibble of the 3 bytes to work out what their queue number is. So they can't really change that. They've got to transmit 3 bytes, and the last nibble has to be the queue number. So all they can change is the 2.5 bytes before the queue number. Unfortunately, I don't have the master module to be able to say this is absolutely what's going to happen. But for me, this looks logically the easiest way of doing it. Now, of course, if you use the whole byte, you get 255. So in theory, if you were to program this, say, in Arduino rather than using a master controller, you could actually have 255 as your full number, which means you could have over 3,000 queues under your control, rather than the 1,200 queues that they use up to the 100 districts. So anyway, that's just a quick video on districts and how I think they are running the districts. I'll carry on and do a follow-up to this if I find anything interesting about those extra bytes which I haven't yet figured out on the 3rd generation and the 1st generation. So just a quick thing, sorry, to finish about why this is important. Well, because obviously we can reproduce the districts when you get greater than 12 queues, because that's the problem at the moment, is that if you've got a 12 queue remote, you can only fire up to 12 queues, whereas if you've got, like myself, where you've got 4 DB04R modules, you'd actually really want 16 queues. But you can't do that at the moment on the current control without making pairs. You could also design your own software for the DB04R module, and you could use your own timings.